Hello again. Thanks for joining us on Space Nuts, where we talk astronomy and space science each and every week, twice a week, in fact. My name is Andrew Dunkley, your host. It is good to have your company. Coming up on today's episode, we're going to get the latest from SpaceX, and they've got bigger and better plans as well. What about low-cost space telescopes? Well, there's a man we're about to speak to who knows all about those because his university's involved. Another weird exoplanet has been discovered and magnetic field issues here on Earth. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us once again to talk about all of that and plenty more, I'm sure, is Jonti Horner, and he is a professor of astrophysics at the University of Southern Queensland. Hello, Jonti.
Good morning. How are you going?
I am well. What about you?
Oh, not too bad. I'm recovering. I just spent a weekend on the Barrier Reef doing outreach. I've got a lovely friendship with a small island at the southern end of the Barrier Reef that I've been going to for 13 years or so. And so Fred gets to go jetting all around the world and go to Scandinavia, and I get to go to the Barrier Reef, which is still really, really awesome, to be honest. So I went out there and did an outreach talk and some stargazing every night, was reminded of the fact that the most distant object I can see with the naked eye is not the Andromeda Galaxy, but is the Triangulum Galaxy, which is very obvious to me from a dark sight. Fainter than Andromeda. That's actually my background at the minute.
Oh, lovely.
Photographing it from home a few weeks ago. I am very, very keen at some point to try and find Centaurus A with the naked eye, which I'm reliably told that some people with particularly eagle eyes can spot from here in the Southern Hemisphere. But for me, Triangulum's it, not Andromeda. We've all seen Andromeda. Yes, so that was great. But then today has been a little bit feral because there have been a few articles gone out about the Orionid meteor shower, which we mentioned on the podcast a couple of weeks ago.
Yeah.
And so suddenly the journalists have realized it's happening today and have been wanting to talk about it today. And I've been trying to disappoint everybody and make Australians miserable by pointing out that it's not the awesome spectacle that some of the AI garbage would have you believe.
Yeah, of course. And there's plenty of AI garbage these days, and it's just getting worse.
Some of the AI-generated images that are popping up on Facebook, I mean, they're pretty, but they're pretty in the same way that a Picasso painting is, in that they don't really bear much reality to the reality that we see. They're rather totally speculative, and it makes me a little bit sad that they're convincing enough, even though they're incredibly wrong, that people who don't know much about the subject get really hyped up and then get really disappointed.
Yes.
So I think that's the damage in it. It's the boy who cried wolf syndrome, right?
Yes.
Here's this amazing thing. It's going to be brighter than the midday sun, and then you can't see it except if you've got a telescope. People go, well, why should I have a look?
Yeah, absolutely. And that's just going to get worse. I don't know how you stop it. There's too many buffheads out there who just want to stir people up. But
I wonder whether it's going to be one of these things that booms and then collapses and reaches a steady state, partially just because of the incredible costs involved with the AI and, the energy use and the water use that everybody talks about. I wonder if it's going to be a thing that's like the lady's shiny toy at the minute and everybody's using it. And then it'll just fall by the wayside a little bit. I guess like auto-tune and pop music and stuff like that. I remember a while where every pop hit that turned out on the radio seemed to have these weird distortions in it because everybody was fond of auto-tune. And nowadays people would rather prove that they can sing themselves rather than have the computer do it for them.
Yeah. Well, I remember a radio interview on an entertainment segment when I worked for the ABC years ago, probably going back 20 odd years or more. And the expert, in inverted commas, was asked if reality television had a future. And she said, no, it'll phase out in 5 years. No.
Yeah,
I think it's the dominant format now.
Oh, makes my head hurt. But I often say this when I'm talking about the search for life elsewhere and the fact that we're basing all our assumptions on knowing one form of life, which is Earth life. Very diverse, but only one form of life. There's an old saying that I'm probably paraphrasing, is that the one prediction you can make with certainty is that all predictions will be wrong.
Yeah. And that one's right. Yes, indeed. We better get down to it. And our first story, or first couple of stories, in fact, involve SpaceX. They've made the news again with a recent touchdown that has been quite spectacular. But they've got bigger and bolder plans, which we'll get to shortly. So tell us about this. I watched the video. It's quite an amazing feat of engineering, isn't it?
It is. And it's a reminder that the development of rockets is done through explosions, and SpaceX are very aggressive with that. And there was a lot of humour had earlier in the year about the incredibly expensive firework displays they were putting on for people of the Caribbean, where there were 3 SpaceX test launches on the trot that went boom in what SpaceX described as rapid unscheduled disassembly.
I love that.
It apparently started as a joke and became a meme, and now is just a standard term, which is kind of adorable in itself.
Yeah.
And at the time, even though there was a bit of fun to be had, and there were some concerns as well, because debris was found across the Turks and Caicos Islands, and there was a lot of controversy about who owns it, who should clean up after it, all the rest of it. All the way through, there's this ongoing line that this is how they learn. This is how you develop rockets. Is you test them to destruction, and from the destruction, you learn more than you would do from a successful flight. And SpaceX have done this all the way through their long history. And they've had a much more aggressive testing schedule than you'd be used to if you think back to the rocket launches of bygone eras where governments were in charge, where every time something went wrong, there was this huge delay where they were painstaking in trying to figure out the nitty-gritty and everything about it. With the way SpaceX have worked, they've got the next rocket under construction when they launch the current one. So there's this rapid turnover of lots of testing, where the goal is not for the next test to necessarily be a perfect success, but rather to be better than the last one. And what we've seen with the last 2 launches of their Starship, of their big headliner rocket that is destined to be the one to launch people to the moon and to Mars and beyond, is the benefits of this kind of process. We've just seen the 5th Starship launch of the year, and the second one which has gone well. And it's the final launch, incidentally, of this version of Starship. They're now working on a bigger version that's slightly taller and slightly gruntier, which will do some more testing, and then they'll build an even bigger version, which is the one that they hope to do a lot of the really exciting stuff with. But the current launch happened about a week ago now, was live streamed, and there is beautiful video footage of it online, particularly of the final stages of the relatively soft, gentle landing in the ocean. And what they achieved with the launch was successfully launched. The boosters, I believe, on the sides came back and touched down on the pad, which is an incredible technical achievement when you think about it, and we now almost take it for granted.
Yeah.
And that's part of the achievement that has allowed SpaceX to launch things to space much more cheaply than those previous government missions I mentioned, because you can reuse parts and that lowers the cost dramatically. But then the same body of the Starship did this suborbital flight, probably, in all honesty, delayed some Qantas passengers flying from Australia to South Africa because they say, we're going to launch a rocket. And of course, you don't want an aircraft to be in the way when it's coming back down. And there were a lot of stories about that earlier in the year, with disgruntled Qantas passengers being delayed when launches were scrubbed. So their flight was delayed and the launch didn't even happen.
Yeah.
This launch definitely did. It flew this suborbital flight, did a few test deployments of satellites to prove it could do that, then re-entered the atmosphere, and there's this gorgeous footage of the thing falling sideways through the atmosphere, not out of control, not tumbling, but looking like it's coming in sideways and like everything's done and it's just going to crash. And then suddenly the engines turn on and it stands on its tail and just slows down until it kicks up all this steam, all this water, but essentially just gently settles onto the water and has a soft landing where it can be recovered and reused. And that soft landing happens somewhere to the west of Western Australia in the Indian Ocean. And it's a really incredible technical feat. I will bag SpaceX when we're talking about Starlink, while I acknowledge that that does a lot of good as well. It's one of these things where it's not all good, it's not all bad, but there's aspects of both. But I think this kind of success should be really celebrated, because it's a really fabulous example of this constant progression of improving technology we're getting that will make human use of space cheaper in the future. It'll allow a lot more variety in what we do. And the context here, of course, is that SpaceX have a contract with NASA to launch astronauts to the moon. And the accelerated plan for that is that the Artemis 3 mission is scheduled to launch in early 2027 to send people out to the moon to do a lap of the moon and bring them back, and probably spend even up to 30 days in space, quite a lengthy mission.
Yeah.
That will be launched off the next generation of this Starship, or the next but one generation of this Starship. And the fact that they've now had 2 launches on the track where it all worked and nothing blew up is probably fairly reassuring for the people who plan to sit on top of this thing in 12 or 18 months' time. It's also something where there's a bit of extra pressure from the big head guy who didn't develop the company but bought it and has been a good advocate for it. I think you'd possibly say in the form of Elon Musk. Challenging individual, but he's really very vocal about the fact that he wants this thing to not just send people to the moon, but also to send them to Mars.
Yes.
And one of the things he wants to achieve in the tech demonstrator phase of that is to use Starship version 3, which is a version after the next version, to launch a mission to Mars, sending small spacecraft robots effectively in the next launch window to Mars. Now, that next launch window is only 12 months away. For those who are keen at looking at the night sky, Mars is almost now hidden behind the sun. It's pretty much out of view. And we're swinging back around to gradually approach it again. And by this time next year, we'll see the usual flurry of activity as people start to launch their spacecraft, and you get the next wave of things going to Mars because that's a cheap and quick time to go there.
Yeah.
That's the launch window. And Elon Musk wants version 3 of Starship ready so that it can launch things to Mars in that launch window to demonstrate the capacity of getting things there with a rocket big enough to eventually put people there. And of course, he's famously expressed the desire to be the first person to die on Mars. I'm sure many people in the audience have similar aspirations for Elon Musk.
Yes, I'm sure. We've had a few comments over the course of the last several months.
Absolutely, but this is where things are looking, and the fact that they've been so successful so quickly is really promising for the moon missions and for the Mars missions to come down the future, and it should be celebrated. And the footage that's out there that you can find all over the place on YouTube is really astonishingly incredible. To see the control this rocket has, and the fact that coming back through the atmosphere, falling on its side, it can suddenly just wake up, stand on its tail, and gently touch down in the water. That's really cool.
It is very, very cool. It sort of goes back to the early days of science fiction where that's what rockets did.
Yes.
And now it's real. So much stuff seems to be happening that has been written about by science fiction writers, 50, 100 years ago. So this new version of the spaceship is going to be, as you said, bigger and gruntier. It's going to have some really powerful Raptor engines attached to it, and it'll be quite an awesome piece of machinery. Biggest rocket ever, I think.
Absolutely. And it would not surprise me if there were a few explosive disassemblies of this one as they tune it up, because that's how they learn. And I think there were a lot of people who are not tuned into this, who are not quite as big a space fans as we all are, who, when the explosions were happening, were taking a lot of mirth from it and saying, come on, they can't even launch a rocket, and we've been doing it for 50 years. And a lot of the voices on the internet who follow how these things go, who are much wiser and much more knowledgeable about this than I am, were saying, don't panic, this is exactly how SpaceX do business. They're not worried. This is how they learn. And each failure happened later, and now they get successes. It's how they work, and it's how you learn. You learn more from your failures than the success.
Yes, they could well be sending a fleet of these Starship V3s to Mars next year, the way they're talking. So watch this SpaceX. Boom, boom. Let's move on to our next story. This is one that your university's a little involved in, and this is low-cost private space telescopes. Do tell.
I do love this. Now, I can immediately take a total detour here because I'm good at that. Here's a topic, and I'm not going to talk about it for the first few minutes, but we have at UniSQ something I'm really proud of, which is our Minerva Australis facility. And that is something we've built to find planets around other stars and learn more about them, to basically work following up the observations of the NASA TESS mission. And we were able to build this facility, which is the only professional astronomical research observatory in Queensland, using Australian Research Council funding and using input from partnering universities. And we're talking about a total budget here of a few million Australian dollars, less than 10 million. If you went back even 20 years, this would not have been possible. What we've been able to do is build this array of telescopes where all the telescopes have 70 centimeter mirrors. So they're big, chunky research grade telescopes that we were able to buy off the shelf because there's a company called Planewave who developed what is essentially the Model T Ford Revolution for research level telescopes, where they realize that there's a really big market for telescopes that are big compared to what amateurs use, but at the small end of what professional astronomers use. And there's a big market because the military wants these to be looking for space debris and to do space situational awareness, satellite tracking, things like that. The wealthiest of the amateur astronomy community want these to do their astronomy with, and that professional astronomers would want to use them as well. And by setting up a production line where you produce these things relatively en masse, rather than getting an order for a telescope, designing a specific telescope for that telescope's needs, and building it as a one-off, you can build things on a production line, and you can make them a lot cheaper, in this case about an order of magnitude cheaper. So that meant we were able to get these telescopes of this size and of this quality for about $250,000 each, instead of $2.5 million each.
Wow.
Which meant that we were able to build this facility and build a relatively low-cost research facility for one task. And that's in real contrast to most of the really big expensive observatories historically, which have been really expensive and all singing, all dancing to do all things for all people.
Mm-hmm.
By having this kind of Model T Ford revolution where you suddenly have telescopes coming off a production line, you're able to make things an order of magnitude more affordable. And that allows people to be innovative and develop bespoke observatories that do one thing well rather than everything well. And they can do that a lot cheaper. And that's been a huge success for us. We've discovered about 40 or 50 planets. We've been involved in the discoveries, all at a really low cost, which makes this probably the cheapest exoplanet facility on the planet in terms of cost per planet learned about. So we're really proud of that. And working on that, we learned about a company in the UK called Blue Sky Space Limited. And they are a very innovative spin-out from University of London. And my name's done total blank there. It's not the Royal Holloway University of London, but it's one of the big universities in the middle of London. We've worked with them closely. We've had Giovanna Tinetti, who's one of the world's leading scientists from them, visit us on us a couple of occasions. And there's this spin-out that came out of their undergraduate master's program where people have set up a company that has looked at the idea of building things on a production line and said, can we apply that to space telescopes? Instead of looking at building James Webb, which is billions of dollars for an enormous, really complex thing that everybody has to fight to use.
Yeah.
Can we take the parts that are available to us off the shelf from people making satellites, and particularly making things like CubeSats, which are designed to be easy to put together, cheap to put together, because you can go and get pieces off a shelf? And can we effectively crowdsource from research institutions cheaper, more specialized space telescopes that are built off the shelf and reduce the costs of building space telescopes by a factor of 10 to 100 times? The first of these that they came up with is a project called Twinkl that I know for a fact we're one of the universities that's bought in on. And that's going to launch a telescope with about a 70 centimeter mirror, so comparable to the ones we've got at our facility, for a cost of about $75 million all up, as a real exoplanet tool. Now, $75 million sounds expensive, but to launch a space telescope of that kind of caliber for $75 million is utterly unheard of. And the way they're doing it is by building it from off-shelf materials. They're getting universities to buy it, and those universities get guaranteed access, and they get to participate in the design, so you get the telescope that is good for the science you want to do. That's going to be Twinkl, and Twinkl is going to launch at some point in the next couple of years. But they've also been working on what was developed second but will launch first, which is a smaller, even cheaper instrument called Mauv. Now, we've been involved in the discussions with this since it was first a thing, but I don't, off the top of my head, know whether we've got buy-in or whether we're observers on the sideline cheering them in, because I'm not personally involved with the mission. But Mauv is a CubeSat. It's going to be about the size of a small briefcase. It has got an off-the-shelf UV instrument, so ultraviolet, looking at wavelengths shorter than we see with the unaided eye, that they've been able to modify to allow it to be a spacecraft that is dedicated at studying stellar flares, looking at stars like the sun, stars like red dwarfs like Proxima Centauri, and studying them to look at how active they are, learning more about their activity levels. Now, this is really interesting in the context of exoplanets and the search for life elsewhere. That's one of the big motivators of this, because there's this idea that stellar flares and stellar activity could be something that makes a planet that would otherwise be really suitable for the search for life and suitable for life to develop and thrive, and turn that planet into a barren and hostile wasteland. And Mars is held up as an example of this. Mars has a very thin and tenuous atmosphere. Now it's cold and arid. But when it was young, it was warm and wet and had oceans and would have looked almost like a mini version of Earth 2.0. It had all the conditions you need for life. But over billions of years, Mars's atmosphere has been whittled away from the outside in by solar activity, in part because Mars doesn't really have a strong magnetic field. Now, it's also lost the atmosphere chemically to the surface. But this has always given people an idea that stellar activity can strip the atmospheres of planets and render them unsuitable for life in the long term, as well as in the shorter term, that extreme activity would lead to UV doses that could even break through and sterilize the planet. So there's a lot of ways stellar activity could be bad for life. What we know about with the sun is the sun's a really calm and chill star. It's much less active than the majority of stars are. And that has led to people speculating along the lines of the anthropic principle that we're only here to observe the universe because our sun is so stable. And therefore, we should only ever look at stars that are really, really stable. There are others who argue that you can't take every coincidence about our solar system and assume that it's a requirement for life. And maybe it is just coincidence that we happen to be around a really stable star. But if we want to learn more about planetary systems around other stars, and particularly if we want to be able to focus the search for life elsewhere on the planets that are the most promising targets, we want to maximize the chances of those planets having life and being suitable for life.
Yeah.
It's really important to learn as much as we can about the star, the planets themselves, all that kind of stuff. And that's where Mauv comes in. Mauv is ridiculously cheap for a space telescope, to be honest, because it's one of these CubeSats made from off-the-shelf materials. It's got this off-the-shelf UV detector that's been modified to do stellar activity work. And it's going to launch potentially in the next month.
Ooh.
Possibly as soon as that. Really, really exciting. And what it will be doing is looking at stars and studying their stellar flares, studying their activity, to give us a really good handle on the diversity of stellar activity you get from planet-hosting stars, and to start teaching us about how those flares could interact with the planets that those stars host. Ties into theoretical work that colleagues of mine at UniSQ have been doing for years, using the kind of modeling software that people use to model space weather in the solar system and trying to apply that to stars that are not the sun and planets around them. This will give the observational grounding for that theoretical work so that people can get a much better handle on whether this assumption we've got based on the one planetary system we have is actually worth following, whether it's less important than that, whether it's more important than that. And so we're going to learn a hell of a lot about stars and also habitability and help direct our search for the most promising targets for the search for life. All from a company that's just innovatively saying, instead of trying to build James Webb at incredible cost and having astronomers from all disciplines fighting for it, let's build something off the shelf with much cheaper components at a much lower price. Build it in such a way that it's good at one thing. Rather than being good at everything, it's good at one thing and one thing only.
Yeah.
And get those people who want to do that one thing to contribute to the cost of launching it. And it is like a space version of what we've done with Minerva Australis. And we know with our facility just how successful that model can be. We've really punched above our weight because of being able to do that. And Mauv and Twinkl, which will follow, are a really interesting window to a future where instead of everybody fighting for Hubble or everybody fighting for Spitzer or James Webb, different research teams have smaller, cheaper instruments dedicated to the work they want to do, and science advances that way instead. There'll still obviously be a place for James Webb and telescopes like that. They will do things that you could not do with an instrument this small. But what this will also do is it will mean that there's a little bit less competition for those jack-of-all-trades facilities, because people who want to do a specific thing may have another option that is cheaper and easier for them to get time on and reduces their contribution to the burden on the other scopes. So this will doubtless indirectly benefit people doing very different science because they get more time to do their science because their competitors are getting time on telescopes in other ways.
Yeah. Could this
just awesome for many, many different reasons?
Yeah. Could this lead to a total rethink of how space telescopes operate? Like, could there be a group that says, okay, we want to specifically search for, X in space, We need a specific kind of telescope to do that. If you build it, we will come, send it into space, and we can do our job. Could it lead to that kind of thing?
I think so long as the price is right.
Yeah.
And that's the thing. If this was no cheaper than building James Webb, nobody'd be interested. But Twinkl will be a fairly big space telescope. 70-centimeter mirror is not to be sniffed at. That's a fairly chunky piece of kit. To build something like that at a cost that is what I said, about $75 million, when James Webb was more than $10 billion, that is a factor of 100 difference in price, effectively. Something like that. Now, 100 Twinkls would not be able to do the same science that one James Webb does, but 100 Twinkls could do a lot of very diverse science. And so it achieves different things. Now, there are other things out there. We've got an interesting one in that there is a partnership between my university, UniSQ, through this iLaunch initiative that's an Australian thing, with the University of South Australia, with Optus, with the Australian National University, and with a couple of startup companies in South Australia, where there is an Australian sovereign satellite that is in the construction under what's called Project Swift. And this is going to be about a $50 million project. That is going to be a satellite where Optus are interested because they're going to be testing technology for better telecommunications, and also a telecommunications platform that are Australian-owned for Australian citizens, so you're not at the whim of people from other countries who may have the ability to turn off your network, as we saw with Elon Musk turning off Starlink over Ukraine at one point because he wanted to. We are concerned about that, so Optus are thinking, well, let's try and have an Australian communications platform. Our involvement is that if you've got a satellite going around the Earth looking down, the backside of that satellite's looking out to space. What if you put a space telescope on the other side of the satellite? You can have a satellite that's doing telecoms in one direction, whilst also providing research capacity in the other.
Yeah.
So UniSQ is leading the research telescope side of that, and my colleague Duncan Wright, who's the head of our Centre of Astrophysics here, is heavily involved in putting together this innovative, fairly small 20-centimeter type telescope to do a little bit of exoplanet work off the back of a commercial platform designed for something else. And that's a really interesting partnership now.
That is.
It all ties back to the commercial launch capacity that SpaceX have provided. Suddenly you've lowered the price of our access to space to such a level that people can now be really innovative and think of new solutions.
Love it.
The downside is more satellites, more light pollution. The upside may be more cool research.
Yeah. There's a price to pay for everything, I suppose.
Yeah.
Okay. Keep an eye out for that, and watch out for Twinkl launching soon. This is Space Nuts with Andrew Dunkley and Professor Jonti Horner.
3, 2, 1.
Space Nuts.
Okay, moving out into the realm of exoplanets, as we've been discussing, and another weird one has been found. We found one similar to this, but this one's a little bit different because it's not where you might expect it to be.
Yes. One of the things that we can do when we're finding planets under the stars is we can learn more about them if we can study them with more than one technique. So going back to the real basics, the two most successful ways of finding planets under the stars are the radial velocity method and the transit method. And the radial velocity method is where you see a star wobbling towards or away from us using the Doppler effect. Mm-hmm. The size of that wobble tells you the mass of the planet, roughly, although we don't really know the tilt of the orbit. So it gives us a minimum mass for that planet. The bigger the planet is for a given wobble period, a given orbital period, well, rather the more massive a planet is, the bigger the wobble will be. So that gives us about the mass of the planet, but it doesn't tell us anything about its diameter. So you can't tell whether it's a Jupiter mass ball of iron or a Jupiter mass ball of feathers. They'd have the same gravitational pull, the same effect on the wobble. Then you have the transit technique, which is where you have a planet going in front of a star from our point of view and blocking some of the light. And the bigger the planet's diameter, the more light it will block. So this doesn't tell you anything about the mass of the planet. It could be a Jupiter diameter ball of feathers or a Jupiter diameter ball of iron. It would block the same amount of light. But it does tell you about the size, the diameter.
Yep.
If you can do both of those methods for the same object, you can get the mass and you can get the size, which means you can get the density. And that's allowed us to identify that planets have a much, much, much greater diversity of densities and compositions than you'd ever have imagined based solely on the solar system. We found planets that are less dense than cotton candy. We found planets. There's one peculiar one that is so much denser than osmium that people think it is actually not a planet at all, but it's actually a planet-sized fragment of a white dwarf that was smashed into pieces. I mean, how weird is that?
That is weird.
So something the size of the Earth, but 150 times the density of water, which breaks physics.
Yeah.
We find all these things, and the only way we can tell that is because we can measure the mass and the size. The planet that we're talking about here, which is TOI 4507b, and what that barcode means is it's Test Object of Interest. It's the catalogue. It's Test thinks there is a planet around this star. This is the 4,507th object listed in the catalogue of Test thinks this could be a planet. And the B means this is the first planet found around that star. Mm-hmm. That's what the barcode means. And the team that has announced the discovery of this planet have done some work using a variety of instruments. They've used NASA's TESS mission. They've used some telescopes based in Antarctica. And it's allowed them to do radial velocity observations to measure the size, and it's allowed them to do transit observations to confirm the diameter. So we've got the mass and the diameter. And that has shown that this is a planet that is about the size of Saturn, about the diameter of Saturn, but a third of Saturn's mass. It's only 30 Earth masses, but it's 9 times the Earth's diameter. And that means the density of this thing is really low. The density is less than 0.3 grams per cubic centimeter. It's less than 30% the density of water, which is really fluffy. That's really, really low density. And that means that in the standard parlance that people have accepted these days, this is classified as a super puff planet because it's all puffed up and light and fluffy and very distended. Now, we think we understand how superpuff planets form in the main. They're planets that are usually very close to very young hot stars, often moving on orbits that are not perfectly circular. And so what's happening is that these planets formed further from their stars. They were flung inwards, probably through interactions with other planets, initially on quite an eccentric orbit, and they're undergoing what we call tidal circularization. So their orbit was extremely elongated, but they feel very strong tides when they're near their closest point to the star and much weaker tides when they're further away. And those tidal effects are acting to make the orbit more and more circular by essentially pulling down that point where the planet is furthest from the star and dragging that inwards. Now that circularizes the orbit, but it also dumps an enormous amount of heat into the interior of the planet, which makes it puff up. The gas gets hotter, so the planet becomes very distended. And in many cases, this makes the planet so large that the outer atmosphere is getting stripped away. And I know colleagues of mine at UniSQ have done studies of some planets like this using James Webb and shown that those planets have tails like comets do because the outer atmosphere is blown away by the stellar wind and they've got an enormous spectacular tail. So in many ways, you can think of these as the biggest comets in the universe. Most of these planets, though, we know are really close into their stars. And the strength of tidal heating is a really strong function of distance. It's not just 1 over distance squared. It's something like 1 over distance cubed or 1 over distance to the power 4. So that means if you move a little bit further away, the influence of tidal heating falls off very, very, very rapidly. So we normally expect to only find these superpuff planets really close into stars. This one is one of the most distant superpuffs ever found from its host star. It's orbiting an F-type star, so that's a star a bit hotter, a bit brighter, a bit more massive than the Sun. But it goes around that star every 107 days, which means that it is further from that star than Mercury is from the Sun. And that should be too far away, really, to have significant tidal heating going on to make this planet bigger. So that's problem number one. That's a little bit weird. The other thing that's very weird of this is that during the process of doing the transit observations of this planet, they also did some Rossiter-McLaughlin observations. Now, this is a really quirky but very beautiful thing that you can do with binary stars and with exoplanets.
Yeah.
Now, with radial velocity, we're measuring the star wobbling towards and away from us. But that star itself is rotating, and young stars rotate quicker. So if you imagine that star, one side of that star is coming towards us, and so the light from that side of the star will be blue shifted. The other side of the star is rotating away from us, and that side will be red shifted. And what that means in actuality is that each spectral line from that star is not a perfectly thin line, but it's actually quite broad. Some of the light is bluer, some of it's redder, so you get this chunky, broad spectral line. And I appreciate for people listening, you can't see me cupping my hands, but I'm waving around helpfully in front of the camera here, even though you can't see me. So the star's rotating, and the star's rotation speed is really much, much greater than the scale of the wobble you get from a planet going around that star, if that makes sense. The planet going around the star makes a wobble measured in meters per second. The rotational velocity of the star is measured in kilometers per second. When you've got the planet going around that star, if it is blocking part of the light from that star, it will be blocking light from one of the two sides of the star that is either coming towards you or away from you. So it's blocking light that is either blue shifted or red shifted. So if you measure the position of the spectral lines from that star while the planet's in transit, if it's blocking some of the blue shifted light, then it will look like the light from the star gets red shifted by several kilometers a second, because you're only seeing the red shifted light, or you're seeing more of the red shifted light. And as the planet moves across, it will then block the other side of the star, and the star's light will appear to suddenly become red shifted. What this allows you to do, it's really intricate, and there's some lovely video explainers on the web. If it's making your head hurt trying to understand me talk through it, there's some really good visual explainers out there. But what this allows you to do is if you measure the radial velocity of a star during the transit of a planet, it allows you to work out the tilt of that planet's orbit relative to the plane of the star's equator. So if the star is perfectly above the equator, the planet is perfectly above the equator of the star and going in the same direction as the star, as it comes round, it'll first block the side of the star that is blue shifted, that is coming towards us, so the star's light will get red shifted. Then it'll move across and block the red shifted light, and the star's light will be blue shifted. Then the transit will end and you'll be back to where you started from, so you'll get this weird kind of sine wave type shape. If the planet's going around backward, that will happen in the opposite order. If the planet's orbit's really highly tilted, you'll make the Rossiter-McLaughlin effect measurements, and you'll only get one or the other effect, or you might get no effect at all, because it's coming down vertically and always blocking the same side of the star.
Yep.
So what this means is that you can use this technique to measure the tilt of a planet's orbit around its star. And again, we've used that fairly effectively from Mount Kent with our wonderful facility we've got here. It's become a really common tool in the arsenal of planetary scientists. And it's revealed a lot of quirky things. So planets around stars like the sun, or planets around stars that are cooler than the sun, typically tend to be aligned above the equators of the stars going around prograde. But when you get to these really hot stars that are more massive than the sun, there's a growing population of planets we've found with very heavily misaligned, very heavily tilted orbits. And that's really odd, but they tend to be the hot Jupiters. Most of those really tilted orbits are planets really close in. Excuse me with my phone making a noise there. I should really have put that on silent, but I normally would do.
Yeah, it reminds me I haven't put mine on silent either. There we go.
Yes. Naughty, naughty, naughty. I will call that person back a little bit later on. I suspect they want to talk about the Orionids, because that seems to be what's happening all the time at the minute. But anyway, what I was saying is, essentially the more massive stars seem to have, a subset of them have these really heavily misaligned hot Jupiters that are all really close in. But we normally only find them when planets are really, really close in. This weird superpuff planet that is a superpuff despite the fact it's too far from its star to be a normal superpuff, it's one of the furthest we've ever found, is also one of the most distant planets from a star that we've ever found on such a misaligned orbit. Its orbit is tilted by 82 degrees to the plane of its star's equator.
Wow.
So it's almost up at right angles. So I know that was a lot of long explanation, but you've got a planet with two things that are very, very unusual about it at the same time, which leads to the obvious thought that maybe these two things are linked. And maybe what we're seeing with these two things is kind of cause and effect, or something that's telling us about the history of this planet, about how it's got onto that extremely tilted orbit. Maybe it's telling us that the encounters and the stirring that have flung it onto that orbit are relatively recent, and they've caused a lot of tidal heating. So the superpuff nature of the planet is an artifact of its recent transition to a totally new, highly tilted orbit, maybe through very close encounters with another planet that's been ejected from the system. We just don't know yet. This is a weird thing. In a lot of ways, this thing doesn't fit the models of how we'd expect most superpuff planets to look, how we'd expect most highly tilted planets to look. And that makes it hugely exciting for scientists, because it's allowing us to get a window into rare things that might not normally happen.
Yeah. So just a quick question to finish this one off. If that planet is basically rotating on the vertical around the sun, would all other planets orbiting that sun do the same thing, or could they be on an equatorial orbit, if there are any?
That's the kind of question we want to answer. I mean, getting to a highly tilted orbit can happen a number of different ways. So there's a few different models for how this could happen, and they're not mutually exclusive. One way that you can pump up the tilt of a planet's orbit is through close encounters between planets stirring each other up. However, that's not that effective. And I know that coming from a solar system astronomy point of view, comets coming in that are scattered by planets very rarely get their orbital inclinations changed dramatically in a single encounter. That's really hard to make happen. You can set it up so that it does, but that's going to be quite rare. There is another effect that you can get, which can work with that, called the Kozai effect, where once you've got two objects that are massive, inclined by about 30 degrees to each other, you can get this periodic exchange of energy or of momentum between the eccentricity and the inclination of an orbit, and you can cause it to oscillate from having a low eccentricity and highly tilted orbit to a high eccentricity, low tilt orbit relative to a given plane. And what that can do is it can cause the object to go from a nearly circular orbit at a relatively low tilt to a higher tilt and more eccentric orbit, and back and forth, oscillating back and forth. Then you can decouple the planet, because when you're on the highly eccentric orbit, you get close enough to the star to get that tidal circularization process we were talking about, drop it out of that resonance, trap it at that high inclination orbit, and then it becomes a more circular orbit. And what that would do would leave you with two very misaligned objects that are very, very widely separated. The third option, and this is one that my old boss at the University of New South Wales many years ago, which he favoured, was the idea that the angular momentum vector of material coming in when the star forms, everybody just assumes that the disk around the star and the material coming in late will be coming in with the same spin axis as the material that formed the star in the first place. And given that you're in a very dynamic and very evolving environment of a young stellar cluster, that's not necessarily the case. And so you can imagine a situation where a star forms with a disk that is very misaligned to the star, and then the planets form in that disk. And then all the planets will be in the same orbital plane, but they'd be very misaligned with the rotation of the star. So these are all different models, and doubtless all of them have happened somewhere. And what we want to learn is how common they are, how they work, so that we can get a better handle on planet formation. Because what all these kind of discoveries remind us is that A, planets themselves are more diverse than we could ever possibly have imagined, but also their orbits and their architectures and the setups of planetary systems are also incredibly diverse. And we're in all honesty just scratching the surface, but finding the oddities allows us to better understand the process by which planets formed, and therefore better understand our own place in the cosmos and how our planetary system came to be.
Interesting. Yeah, the more we look, the stranger the things are that we're finding, and some defy explanation, and this is certainly one of those. So if you'd like to read all about it, you can do so through the archive website.
Okay, we checked all four systems and keying with a go.
Space Nuts.
One final story, and this takes us close to home, and Earth's magnetic fields are acting a little bit weird, and we've got this giant weak spot this is in the Atlantic, I believe, is it?
Yes, South Atlantic. Now, this is one where I will stress that I'm not an expert in magnetic fields. I'm not a geophysicist, but this is still so cool we had to talk about it. And for those listening in who understand this better than I am, please be gracious when you tell me what I got wrong when you comment. But anyway, this work is the result of a group of satellites run by the European Space Agency called SWARM. And they are satellites that are monitoring Earth's magnetic field. And when you learn about the Earth's magnetic field at high school, you basically get this idea that the Earth is this giant bar magnet and has this bar magnet type magnetic field around us, and that's about it.
Yeah.
But in actuality, the Earth's magnetic field is incredibly complicated. And there are areas on our planet where it's stronger than average and areas where it's weaker than average. It has two dominant poles. It's got the North Magnetic Pole and the South Magnetic Pole, but they're not necessarily aligned in such a way that a line between them would run perfectly through the center of the Earth. They are both moving as time goes on. And that's all because the process that generates the Earth's magnetic field is really complicated and is down to moving fluids, moving molten iron in the Earth's outer core, essentially. So you've got this molten ferromagnetic kind of material sloshing around, driving a dynamo that creates this time-varying magnetic field that does all sorts of weird stuff. For a very long time, it's been known that there is this anomaly in the South Atlantic where the magnetic field is somewhat weaker than anywhere else on the planet. Mm-hmm. And this has been, I've even heard it described as being kind of the Bermuda Triangle of space. It's a place where satellites misbehave.
Yeah.
And it's something that space agencies, governments, and now commercial entities are very aware of, because where you've got a weaker magnetic field, you've got less protection from the vagaries of cosmic rays, solar radiation, solar storms, things like that. So it's a place where your satellites are going to be more vulnerable than normal and more likely to throw up errors and have problems. And it's really interesting to study how these things change with time, because if you think about the roiling and the boiling of that molten material in the Earth's inner core, that's going to vary with time. And that's what these satellites have been mapping. And what they've found is that this South Atlantic anomaly, the Bermuda Triangle of the South Atlantic from a magnetism point of view, has been changing quite dramatically. They've been mapping it since they were launched in 2014. So we've 11 years worth of data now. And what they've found is that that anomaly in the South Atlantic has got bigger. It now has got bigger by an area equivalent to kind of Central Europe, Western Europe. So that's a fairly big amount of growth in just 11 years. It's wibbled around. At the same time, the magnetic North Pole is merrily trundling its way, moving from Canada to Siberia. There are a few extra strong patches of the magnetic field. One of those in Siberia is getting stronger and stronger. The other strong patch in Canada is getting weaker, but is still a strong patch. There's one possibly over by India. And so we're getting this impression of the magnetic field of the Earth varying on timescales of years and decades at quite a rapid way, fluctuating probably more than we'd have ever thought of just from ground-based observations. Now, it's interesting from just purely a science point of view to see everything wibbling and wobbling. It's also really important for people launching satellite constellations to be aware of this and to mitigate for it and to plan their orbits around it. Because if you've got one point in orbit around the Earth that is more vulnerable than the others, fortunately it's over the ocean, but maybe you want to have fewer satellites going through that area so that you maximize the lifetime of your satellites in terms of their working lifetime and things like that. So it's useful from that. Now, a couple of the things that have been mentioned in the discussion of this, in all honesty, I don't fully understand how they're connected. One is that the data from these satellites has been said to suggest that that motion of the pole from Canada to Siberia has been happening since the mid-19th century. Now, I think that's probably something that's getting a bit lost in translation, because I'm not sure how observations going back to 2014 can tell you about something that was happening in the 1800s.
Yeah.
I suspect what the authors have probably said in the original paper is there have been suggestions in measurements from the ground that the pole has been moving for all this time. But what we've got now is a very clear model of how it's moved over the last 11 years because we've been observing it. And that somehow got shifted to the results suggesting that motion has been happening for that length of time. I think that's probably a miscommunication thing, because I don't see any way that an 11-year period of observation can accurately tell you what was happening 150 years ago. You need other observations for that.
Yeah.
But, that movement is an ongoing thing. The other thing to probably reassure people, I know people sometimes worry that this means our magnetic field's about to cease and desist and turn around and the end times will come and it will be apocalypse and all the rest of it. This South Atlantic anomaly is something where geological evidence and core drilling and sampling of places where the magnetic field gets frozen in. So if you look at rocks, you can tell what the magnetic field was doing in the past.
Yeah.
That tells us that this anomaly over the South Atlantic has been there in one form or another for at least the last 11 million years. So it's not new and scary.
No.
Rather, we're seeing something that has been going on for a long time, but wibbling and wobbling and is sometimes bigger and sometimes smaller.
It's normal.
This is normal, but it's amazing that we can now get information about it on such timescales. And it's much as it's out of my area of expertise, I think it's yet another of these fabulous examples of how what you get taught at school is a very simplified version of the way the universe actually works. And what we'll learn from science is not always that what you were taught was wrong, but rather that what you were taught was incomplete and we need to learn more. So we've gone from, if you'd asked me as an 8-year-old what the Earth's magnetic field's like, I'd have probably parroted, it's like you've got a bar magnet and the magnetic field has a North Pole and a South Pole. And there's an inference there that it's unchanging. There's an inference that everywhere at the same distance from the pole has the same magnetic field strength, all these things. When in fact, it's a much more dynamic situation than that.
Yeah.
And it's much more like looking at a boiling kettle through a glass window on the side and seeing the water bubbling and roiling around, rather than just looking at the steam coming out and saying, oh, look, there's steam.
My answer to that question at school would have been, the what? Yeah, but it's also indicative of how very active the interior of the planet is. And I read the news every day, and there's particular types of news that I look out for, and one of them's volcanic activity. And there's been a heck of a lot of stuff going on lately all over the planet, but a few places are starting to pop up as active. There's a particular volcano in Iran that they thought was extinct. It's now starting to show signs of waking up. Yeah.
Wasn't one that they don't think has erupted for several million years and is now lively now?
Yeah, there's all sorts of things happening like that. So who knows? The Dubbo volcano may make a comeback. Yes, we did have one here millions of years ago.
Yeah, well, I live in an area on the Darling Downs that's incredibly fertile, and it's incredibly fertile because there was a supervolcano erupting here tens of millions of years ago that fertilized the place. We have got volcanoes in Australia that have been active on the mainland within the scope of knowledge of our wonderful traditional owners here. I think some of the ski resorts in Victoria last erupted since the last ice age.
Yep. The only active volcano in Australian territory is an external Australian territory southwest of Western Australia. I can't think of the name of the island, but that's the only active volcano in Australian territory. But we've got several that aren't far away around Indonesia and of course New Zealand. And
exactly. I mean, we've got the ones that are classed as dormant that have erupted so recently that we know they'll erupt again.
Yeah.
We had this beautiful road trip about 18 months ago where we left Toowoomba, we picked my partner's parents up down in northern New South Wales, and we went all the way over to Adelaide and back around the coast. Coming back up, we did an awesome 3-week trip.
Yeah.
And we stopped at a place I think was called Tower Hill, just on the Victorian side of the border with South Australia. It was a fabulous spot for bird life, had the most amazing view of wedge-tailed eagles and stuff. But that is a relatively recent maar, I think they're described as. And there's a load of these around that area which are not quite mud volcanoes and stuff, but they're not, oh my God, explosive Hawaiian-type volcanic activity, but they're volcanic activity in recent geological time that will happen again. It's all that kind of stuff. Mount Buller, I think, is a ski resort that last erupted about 6,000 years ago. On timescales longer than our lifetimes, the Earth's a much more dynamic place than we think. And this is part of the wonders of working with and talking to people who interface with the traditional owners of the land and do it in a respectful enough way to be able to learn some of the knowledge they've passed down. Because there is oral history passing down memories of these events happening. People on this continent now have a living oral history that recorded events tens of thousands of years ago and have passed them down in a form that we can identify them and learn from them and get a feel for these events that are much rarer than we'd normally observe, even in the kind of nominally modern science period of 400 years.
Yeah.
When you talk about something 6,000 years ago, we can get information about it now. I think that's magical.
It is indeed. If you would like to read about the South Atlantic anomaly and all the stories we've talked about today, you can do it the easy way and go to space.com. Jonti, we're done for another day. Thank you.
That's an absolute pleasure. Thank you so much. And my phone is now on silent. So.
And we've just finished. All right. We'll catch you soon on the Q&A episode. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. And thanks to Hugh in the studio. Couldn't be with us today. He took a ride on a SpaceX rocket and everything was going fine until they came into land. Then he saw a button and it said, "Don't push." Well, this is Hugh we're talking about. So I think you saw that explosive catastrophe. Anyway, he'll be back with us one day after the injuries are all done and dusted. And from me, Andrew Dunkley, thanks for your company. Don't forget to visit us on our website or our social media sites, and you can interact with each other there as well. Until next time, Bye for now.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.